Welcome. Last time during class, we were talking, and one of you asked about, okay, is it more often that gas inside the stars is fully ionized, or is it more often that it's neutral? What's the typical situation? And what we said, and I'd like to pick up a little bit on that discussion, is that if it's hotter than about 10,000 Kelvin, I said 5 to 10,000 Kelvin. I'm actually going to show you a graph here in a moment, which makes this a little bit more clear. Then the hydrogen, at least, will be fully ionized. So let me go ahead and start sharing screens with you. This PDF that I'm about to show you, this was generated by Richard Townsend. He's a collaborator of a collaborator. I met him a few years ago. I've never written a paper with him, but I've written papers with people that have worked with him before and done research with him before. Remember at the beginning or earlier this month, we looked at the Boltzmann factor, and we said that the higher energy states are going to be more well populated the higher the temperature of the gas is. So I'm not going to go through the details of these steps here. I had you skim the reading that had to do with the Saha equation. And what Richard Townsend has done is he's applied the Saha equation, which crudely speaking is just taking the ratio of the likelihood of two states. There you can see the Boltzmann factor where chi sub j is going to be the energy difference between those two states. And the two states he's considering are the ground state of hydrogen and the electron being ripped off of hydrogen. And he goes ahead and solves for the ionization fraction x. And that's what this plot here is showing us. But if you go ahead and you look on the vertical axis, this is ionization fraction. On the horizontal axis is temperature. And right here at the transition, it's around 10,000 Kelvin. So for hydrogen, if you go up to temperatures much more than 10,000 Kelvin, you can see it's basically 100% fully ionized. All the electrons are off. If it's down below 10,000 Kelvin, especially down below about 6,000 Kelvin, then it's going to be much closer to neutral. In other words, the electrons will be on the hydrogen. And so this is a more detailed answer to a question that was asked last time, but it's also a comment about a homework problem that you'll be working on for this week. In particular, remember, one of the things you're going to be asked to do is to calculate the mean molecular weight at the different regions of the sun, at the photosphere, at the center, and so on. And at the photosphere of the sun, the temperature is just shy of 6,000 Kelvin. And so the vast majority of hydrogen is going to be in atomic form. That is, the electrons in the photosphere are going to be down on the hydrogens. In the center of the sun, of course, it's 15 million Kelvin. And so there it's easily fully ionized, as it is throughout most of the star. Now, it's true that if you're at the photosphere at this temperature of 6,000 Kelvin, whether or not an element is ionized is going to depend on what element we're talking about. It's going to be different for hydrogen than it is for calcium or whatever. But for what you're doing on your homework, it's going to be sufficient to make the assumption that you have a neutral gas there when you are calculating the mean molecular mass. Hydrogen is, after all, the largest component. With the hydrogen being neutral, it's going to be good enough approximation to say everything is neutral. Questions or comments at this point about anything? So, photosphere of the sun has neutral hydrogen. That's relevant to a homework problem. Last time, we were calculating the mean molecular mass mu for a fully ionized gas. And we're going to review that quickly, then we'll talk about a neutral gas, and then we'll move onward through chapter 10. But as a reminder, we imagine that we have a little box of gas. It'll have n particles in it of total mass m, and it has mass abundances of hydrogen, helium, and metals, x, y, and z respectively. And we said that the number of hydrogens is going to be the mass of the hydrogen divided by the mass of a single hydrogen, a proton. Here, the number of heliums is the mass of all the helium, y times m, divided by the mass of a single helium nucleus, 4 times the mass of the proton. And then the mass of a metal, of the metals, is going to be Zm divided by AMP, where A is some kind of average atomic mass. 16 is a good number. We're not going to worry too much about the details of having to treat each of the species individually. Rather, we'll lump them all together into just one class of things, metals. And that's appropriate and it's sufficient because this Z is usually very small when you're talking about stars, usually 2% or less. And so if it's a fully ionized gas, then the electrons are ripped off of the atoms and you've got to count them in the count, N. They count towards the number of things in the box. So the number of electrons would be the number of hydrogens, the number of protons, plus twice the number of heliums because you get 2 electrons for each helium nucleus, plus A over 2 times the number of metals that you have, because we're making the approximation that if you have an atomic mass A, about half of the nucleons will be protons and half of them will be neutrons. That's true for carbon and nitrogen and oxygen, for example, in their common isotope forms. And so at the end of last class, we said, okay, the mean molecular weight is the average mass of a particle in the box. That's what m bar is. But it's a non-dimensional quantity, this mu. So we divide it by a proton mass. It's just the standard convention. And so here's that 1 over mp that I just said. And the average mass of something in a box is capital M, the total mass in the box, divided by capital N, the total number of things in the box. And we rushed through this last time. I'm going to just write down here an intermediate step that we didn't have time at the end of class last time to write down, just so you see where that final result comes from a little bit better. But here in the numerator, we have the total mass in the box. And in the denominator, we have the total number of things. Oh, and I forgot to divide by this m sub p right here, so I'll put that in right now. There's the m sub p to make sure that everything's dimensionless in the end. But the reason this says 2n sub h right here is because the number of things in the box is one of these n sub h's plus one of these n sub he's plus one of these n z's, but then we also have to add in all of the electrons' contributions. So there was one NH from before, and here's another NH to give us a total of 2 NHs. And here we have one NHE, but then we get 2 NHEs from the electrons for a total of 3 NHEs. And then we have one of these NZs, and in the electrons we have A over 2 of the NZs. So we have a total of 1 plus A over 2 of these NZs. Now remember, a typical value for an average A is like 16. So 16 over 2 is 8. We're going to neglect the difference between 8 and 9. To make this a little more convenient to calculate, we're just going to say that 1 plus A over 2 is about the same thing as A over 2. That's an approximation that I mentioned last time, but I didn't write it down because we didn't have time. But now you can see it. And then if you look, when you go ahead and plug in for these expressions for NH and NHE and NZ, they're right here and here and here. You see how each of these capital N's has a capital M over a lowercase m sub p in their expressions? And what is in the numerator? A capital M over a lowercase m sub p. So those all make ratios of 1. And what we're left with is this 1 over 2 times x plus 3 over 4 times y plus this A over 2 divided by A gives you a half, so plus a half times Z. And that's the expression we wrote down at the end of class last time for the fully ionized mean molecular mass. What comments and questions are there on that?
I just have a question about the mean molecular mass. Is it an average mass in a small ball of gas somewhere within the star?
Yeah, right. So that is right, and it's in units of the mass of the proton. So think of this box here as being somewhere inside of a big star, right? So it's a small little box somewhere inside of a star. And the box is small enough that it's defining the area locally. But the box is big enough that you have a large number of particles in it so that you can talk about taking averages of quantities.
Okay, thank you.
Other questions and comments?
My question was similar to that. I was going to ask about what size region we usually talk about in this case and how big that region can be. what are the minimum and maximum number of particles we can deal with in a situation like this?
Variations are going to often go like square root of n. So if you had 100 particles in a box, another box of the same size might have 100 plus or minus 10 particles in it. And quantities, usually their errors on them scale like 1 over the square root of number of things you have in the box. So if you wanted a 10% error on things, you would only have 100 particles. But if you wanted a 1% error, you'd have 10,000 particles, 10 to the 4 particles. So you want to have a good number of particles. Maybe you have, an Avogadro's number of particles. And that allows you to make very, very accurate, meaningful statements about what's going on in there. So in practice, if you had something that, it may depend on where you are. As you get out towards the photosphere, you might need to take larger areas. But if you have something throughout the star, if you're in the middle of the star and you take something that's a millimeter across by a millimeter by a millimeter, that's more than enough to be able to have a large number of particles and be able to take meaningful averages in it. I think the thing to think about is whether the quantities change over the length scales you're dealing with. And if the composition doesn't change significantly over a millimeter, then, it makes sense to talk about the composition at that point. And what you're really doing is you are averaging the quantity over a small region surrounding that point you're talking about. And if you start to try to average over something that's 1/10 of a solar radius, well, don't expect any longer that those quantities are going to be uniform over that region. And so it becomes less meaningful to talk about the average at that in those scenarios. Or less helpful, at least, I should say.
Okay, and then the other question I had was, how do we take this information and use it in something like an SPH code?
Right, so an SPH code is a smooth particle hydrodynamics code. And the way those codes work is that you have a star, say, and you break it up into many little parcels of fluid, which overlap with one another, but you can think about each parcel, or what is called a particle, as representing a chunk of fluid from that star. And so each chunk of fluid in that star could be assigned an X, a Y, a Z, and correspondingly, it could therefore be assigned a mean molecular mass. And then if you know the mean molecular mass of a particle, then that's information you could use in the equation of state for a given density of its surroundings and a given temperature that it has. Combining the density, the temperature, and the mean molecular mass could give you the pressure due to that particle or inside of that chunk of fluid.
Thank you, Dr. Lombardi.
Other questions and comments? So I mentioned on the homework you're going to need to know about the mean molecular mass in a neutral case, right, when the electrons are no longer ionized from their atoms or the nuclei associated with them. And so let's go ahead and let's talk about the neutral case, not the fully ionized case. It's an extreme. We're not going to be doing the generalized case of the when it's partially ionized. But the big difference now is that the number of electrons in the box is 0. So if we go and we want to calculate the mean molecular mass, or mean molecular weight, it's m bar over mp as before. That's how mu is defined. And there's the 1 over mp. The average of a particle, the average mass of a particle now, is the total mass in the box divided by the total number of things in the box. And unlike before, where I had to include an NE in the number of things, I don't do that any longer because the electrons are counted as part of these neutral atoms. So a proton and an electron together count as one thing. And so let's go ahead then and plug in. We have these same expressions that we had before for NZ, for NHE, and for NH. And notice how in each of those expressions there's a capital M, also over a lowercase mp. And so when I plug in those expressions for the capital N's, the capital M over lowercase mp is going to cancel with this capital M over lowercase mp. So I'm not even going to bother to write that down any longer. The stuff that remains is going to be the following. I have here for NH, I'll get an X. Here for NHE, I'll get a Y over 4. And here for NZ, I'll get a Z over A. And that's it. That's the result. This is equation 10.14 in your textbook. And as I said last time, this equation down here is equation 10.16 in your textbook. I've written it in a slightly different format, but it has the same information content. So this, remember, was the neutral case up here. And this is fully ionized. Let me ask you a question. Here's the question. I'll write it on the board. For the same X, Y, and Z abundances, which is larger? The mu for fully ionized or the mu for neutral? I want you to try to think about that. See a couple neutral responses. That's right. And the idea here is, does anybody want to say how they knew that was right?
MP is smaller?
Well, no, it's not MP so much that it's smaller, because MP is a constant. MP represents the mass of a proton. But
The denominator, sorry.
the denominator is smaller. Well, yes. Okay, that'll make mu larger. And you can kind of tell that, that's a good point, because here you had only one of each of these things, and here you have more than one of each of these things. So that is a beautiful mathematical explanation for why that's the case. And then intuitively, you can also think about it. When you are ionizing a gas, there's a comment that the electrons have kinetic energy while bouncing around, meaning less energy for mass. Well, it's true that, depending on how you define mass, that mass depends on the motion. But when I talk about mass, I'm going to talk about rest mass energy. So that a particle is going to have the same rest mass regardless of whether it's moving or not. I think you're thinking of good ideas, but there's an even simpler way to envision this. When you go to a fully ionized gas, what are you doing? You're plucking off electrons off of what were previously neutral atoms. And so these electrons are very low mass things that start to count, and they will drag down the average mass of particles. Like, take the simplest case where you just have a single hydrogen atom. The average mass of that one thing is its mass, the mass of a hydrogen atom, which is about the mass of a proton. But as soon as you pluck the electron off, now the average mass is this heavy thing, the proton, with the light thing, the electron, and so the average mass is about half of what it was before, to the extent that the electron has zero mass. And so when you pluck electrons off, you drag down the average mass per thing. Comments or questions on that? Okay, so let's move on to talk a little more about section 10.3 material now. 10.3 is about stellar energy sources. And so, what is it that's powering the sun? One thing you might say is, okay, even if you know what the answer is going to turn out to be, you might say, well, let me consider the fact that as a gas cloud collapses, it's losing gravitational potential energy. just like when I drop something, it goes to lower and lower gravitational potential energies, and it picks up kinetic energy as it falls, right? That potential energy is being converted to some other form. If you have a gas cloud collapsing to form a star, then it's losing gravitational potential energy, and that could give it other forms. It could make it hotter, it could make it radiate. Maybe the radiation from the sun is due to gravitational contraction. Let's test that idea. Now, in the beginning of section 10.3, they go through a slightly more detailed calculation than the one that I'm about to sketch out here. But the basic idea is you can write down as an integral there what the potential energy due to gravitation is inside of an object. But the result is not at all surprising, right? So the idea here is that the gravitational potential energy can be dimensionally estimated and I'm talking about the gravitational potential energy of a star of mass m and radius r. And so you might say, well, I could do an integral and to figure this out more precisely, but what is it going to have to scale like? Well, it's got to depend on the mass of the star and the radius of the star and Newton's gravitational constant. And so that's really the only thing that it could depend on, gm squared over r. Remember, that's an energy. We've seen that gravitational potential energy of interaction, gm1, m2 over r, the minus sign. And so you could work hard to get a better numerical coefficient here than -1. Maybe it's 3/10, maybe it's minus 0.5 or minus 0.2. It depends on how you distribute the mass within the star. But at this point, we're just making an order of magnitude estimate. And so if this is the gravitational potential energy, it's worth pointing out by the virial theorem that we've discussed earlier in the course, that we don't have to just say that the gravitational potential energy scales that way. The total energy in the star is going to be on the order of half the gravitational potential energy in the star. So it's also going to be on the order of minus gm squared over r. This allows us to introduce what's called the Kelvin-Helmholtz timescale. And I can think about the Kelvin-Helmholtz timescale here in two separate but related ways. First of all, the way you calculate this Kelvin-Helmholtz timescale is to take the available energy and divide it by the luminosity. So the available energy here, what I'm talking about is, it doesn't matter because I'm making an estimate, either U grav or E. And I could take that energy and divide it by the rate at which the energy is being used up. Remember, luminosity is an energy per time. So if you take the energy available and you divide by the rate at which that energy is escaping, maybe this is the sun we're talking about. And so the sun has a luminosity of 4 times 10 to the 26 joules per second. So the energy divided by the energy per time gives you how much time it would take to use up the available energy. And one way you can think about this Kelvin-Helmholtz timescale is to say, okay, well, all these energies scale like gm squared over r. The thermal energy, the energy due to the microscopic motion of the gas, is on the order of gm squared over r. And if I'm radiating away at a certain rate, how long would it take for me to radiate away all the energy? Or if you like, you can think about this energy as being replaced by this gravitational potential energy. And there, what you're thinking about is, imagine you have a gas cloud that's originally infinitely large, and it collapses down to a radius r. Well, in that process of collapsing down to this size, this is how much potential energy would have changed by. And that's how much energy could have then be released in other forms, like through radiation. And so you can think of this numerator as being how much energy there is available by taking something really big and collapsing it down to the size of what you have now. And so what are these Kelvin-Helmholtz timescales values like? Well, it depends on the mass and the radius of the star that you're talking about. But let's go ahead and talk about the sun as a particular example. For the sun, T Kelvin-Helmholtz, what do? It's GM solar squared over R solar divided by the luminosity of the sun in this case. This turns out to be about 10 to the 15 seconds, which is about 3 times 10 to the 7 years. Right? 30 million years. And that's a long time, sure, but remember that we have meteorites that have been dated to be 4.5 billion years old, right? The sun is not going to be less old than the Earth and the moon that's going around the Earth. It wouldn't make sense if Kelvin-Helmholtz timescale were the timescale associated with how old the sun is. And so what we're saying is that the luminosity from the sun, it does not make sense to try to explain it from the thermal energy that's in the sun or from the gravitational potential energy that can be released. There's got to be something else going on inside of the sun to explain how it could be around for not millions of years, but billions of years. Comments or questions on this?
So what exactly does this mean then? What does the Kelvin-Helmholtz timescale mean?
This is an important timescale in other contexts. So let's say, for example, you had a cluster of stars, and the stars are colliding in them. So 2 stars collide, you make a merger product that's all puffed up. And you might ask yourself, how long will it take for this puffed up merger product to settle down to something normal again? And the answer is the Kelvin-Helmholtz timescale. And so you collide 2 stars together, you get this big puffed up thing, but on this timescale it'll contract back down as it radiates away its thermal energy to something more like a normal sized star. And, so if you really cared about runaway collision objects in clusters of stars, for example, this is an important timescale to know about, and you can compare it against the time between collisions. Because if the time between collisions is much shorter than this time, then you collide something, it's a big merger product, and the next collision comes along very quickly and you hit it while it's still big. But if the time between collisions is the time scale used for things outside of astrophysics, I would have to imagine, so you might have to recast this in a different context. Let me finish talking about the stars in the cluster and then move on to another example of where you might care about it. But if the time between collisions was much larger than the thermal time scale, then you get this big thing and it contracts before another star comes along. And so the other star coming along has a smaller cross section for a collision because the first star, the merger product, had time to collapse. And you can think about, now turning to the comment that was in the chat, applying the same kind of idea to many different scenarios, right? So for example, I could put an ice cube on a table. Here's a non-astrophysics scenario where I might talk about the Kelvin-Helmholtz timescale. And on a short enough timescale, the ice cube just sits there on the table. It's in equilibrium. Right? If I come back 2 seconds later, it pretty much looks exactly like it looked 2 seconds earlier. But then you might ask, well, what if I come back 2 hours later? It looks quite different. The ice cube has melted down onto the table. It doesn't look like anything before. What's the time scale on which that occurs? Well, if you know sort of the thermal energy content, that would be the numerator. And if you know the rate of energy exchange between the table and the surroundings, the table combined with the surroundings and the ice cube, then you can take the energy content of the ice cube, divide it by the rate at which it's gaining heat from the surroundings, and then you would get some time scale that describes how long the ice cube lives for. Right? And so you can imagine applying this idea. It may no longer take the name Kelvin-Helmholtz timescale, but you can imagine applying the idea of the Kelvin-Helmholtz timescale in contexts outside of astrophysics. Other comments and questions?
Just a clarification, Dr. Lombardi, L in this case is luminosity?
Yeah, that's what L is, the luminosity. So in the case of the sun, this is about 3.8 times 10 to the 26 watts that we would have down in the denominator, and a watt is a joule per second.
Thank you. So what does this 30 million years mean for our sun?
It's a rough estimate of how long it would take the sun to collapse when it was on the pre-main sequence. So out of the gas cloud that you start with, how long does it take that fragmenting gas cloud to form the sun? And it's roughly 30 million years, Kelvin-Helmholtz timescale, to within a factor of a few. Other comments and questions? What is powering the sun then? Does somebody want to shout out? What is the, I think you know. You probably know. What is the power source of the sun?
Fusion?
Yeah, fusion. Exactly. Fusion. And so let's talk about that now. 1, 2, 3, 4 dots to represent 4 protons. And those 4 dots have a total mass combined together of 6.69 times 10 to the minus 27 kilograms. And then 1 helium nucleus, I'll have an open circle and an open circle to represent the 2 neutrons, and 2 dots to represent the 2 protons. And now this 1 helium nucleus has a mass of 6.6, wait for it, 4 times 10 to the minus 27 kilograms. And the point is that it's a little bit less, 0.7% less than the mass of the 4 protons from which it came. And so the key idea here is that inside of stars like the sun, you're converting protons into helium nuclei. And in the process, you're destroying mass. And that mass is being released as energy. So how much energy? Well, remember, E equals mc squared. So if you change the amount of mass by some amount delta m, associated with that will be some energy delta E. And they're very simply related to one another. You just need to multiply the change in mass by the speed of light squared to get the energy released. In this particular case, we're starting with 4 protons per reaction, and we'll talk about, if not today, next time, in a little bit more detail what the reaction is. There's actually a set of steps that take you from here to here. It doesn't all just happen at once. And there are other things that are involved, like positrons and gamma rays and neutrinos. But there's the change in mass, and we multiply that by c squared. And this is equal to 4 times 10 to the minus 12 joules. That's just from making 1 helium from 4 protons. So this is the energy release from making 1 helium nucleus from 4 protons. Now let's estimate the number of protons in the sun. Because if we know the number of protons in the sun, we could figure out the number of helium nuclei that we could make from those protons. And then we could also, if we knew the number that we could make, we could figure out how much energy could be released from making all of them. And so the number of protons in the sun, we'll call that n sub h. Now, I know that the sun is only about 70% roughly hydrogen. And I'm just going to pretend the sun is a ball of hydrogen. I'm not going to worry about effects on the order of tens of percent here. So I'm going to take the mass of the sun, and I'm going to divide by the mass of a single proton, a helium nucleus. A hydrogen nucleus. And so the mass of the sun is 2 times 10 to the 30 kilograms. And the mass of a proton is 2 times 10 to the minus 27 kilograms. And so this is 10 to the 57 protons are inside of the sun. And now, why don't we figure out the energy that you could get from fusion? So E sub fusion. I'm going to go ahead and in this calculation, at this step, put in a factor of a tenth. And this tenth is going to be from the fact that, let's say, if we use 10% of all the hydrogen, what we're going to learn is that stars like our sun have fusion going on in their cores, not throughout their entire volume. And it's really only the innermost 10% of the mass that's going to contribute to the fusion process. If you don't want to put this tenth in now, that's fine. You'll find that there's going to be more than enough energy to explain how the sun shines. But I'll go ahead at this stage and say I'm only going to consider 10% of all the reactions that could occur. And so each reaction requires that there be 4 protons that contribute. So I take the number of hydrogens or protons and I divide by 4 so that I can get the number of reactions that are going to occur as they get converted to helium. And then I'll multiply by delta E. Because remember what we said delta E was? The same 4 times 10 to the minus 12 joules that is at the bottom here. That's just from making 1 helium nucleus out of 4 protons. So I multiply by the number of times that I can do that. And what do we get? Well, it's 0.1 times 10 to the 57 over 4 times 4 times 10 to the minus 12 joules. These 4's make a ratio of 1. And this turns out to be 10 to the 44 joules. When we talked about the energy of just a single interaction, it didn't seem like a lot of energy, maybe. 10 to the minus 12 joules. It's a lot in terms of EVs, but it's a small portion of a joule. But then when we start to take into account just how many times we can do it, we start to see that there are huge amounts of energy that are available. So now, just like we calculated a Kelvin-Helmholtz timescale earlier today, we can now calculate a fusion timescale. We can figure out, okay, for that available energy, E fusion, how long would it take the sun to use it up if it were radiating at its current luminosity? So, as before, you take the available energy and you divide it by the rate at which that energy is being used up. And so this is 10 to the 44 joules divided by a little bit less than 4 times 10 to the 26 joules per second. And so this is about 3 times 10 to the 17 seconds. Oh my gosh. 3 times 10 to the 17 seconds, which is 10 gigayears. Now this G right here, G, which means giga, that means 10 to the 9 or a billion. So this is 10 to the 10 years. Each year is about 3 times 10 to the 7 seconds. So when we do the conversion to go from here in seconds to here in years, we get 10 to the 10 years or 10 billion years. And indeed, that's just about how long we expect the sun to live on the main sequence, as we'll be talking about in more detail, where it fuses hydrogen into helium. And so this is completely consistent with the findings that meteorites, moon rocks are 4.5 up to 4.5 billion years old. And so now it makes sense that we found a timescale larger than the age of things within the solar system. This explains how the sun could shine at a comparable rate to what it has now for billions of years. And if somehow you're able to open it up to have more than just the innermost 10% contribute, then you could go even longer. That won't happen for the sun, but for other stars where there's mixing, you might imagine that over the course of that star's lifetime, it could use up more than just 10% of the available hydrogen. Comments and questions at this point?
I have a question. For a star like the sun, it lives for 10 or more billion years, but for stars that are a lot smaller, like red dwarfs, the same fusion process is happening, but they can live for 1 trillion years. Why is that? Great point.
So what happens is the luminosity of a star actually scales like m to the, it's like 3.6 or 8 or something, but we'll just say it scales like m to the 4th power. So if you doubled the mass of your star, went from 1 solar mass to 2 solar masses, the luminosity actually gets 16 times larger. So luminosities are going up quickly with mass. That's the denominator in this expression. The numerator, effusion, well, we're not going to worry too much about whether it's convection or not and whether it can mix or not. Basically, let's just say the amount of available energy in fusion scales like the mass, right? So you mentioned red dwarfs. Let's say we went to a red dwarf, which is 1/10 the mass of the sun. It would have 10 times less energy available for fusion, but it would go through that energy 10 to the 4 times more quickly. And so even though there's, 10 to the 4 times more slowly, I should say, right? Because it's 1/10 the mass, so the luminosity is going to be 10 to the minus 4 what it is for the sun. And so the time scale for the fusion, it scales like m over m to the 4th, which is 1 over m cubed. So the red dwarf would live 1,000 times longer than the sun. So if the sun lives for 10 billion years, something 1/10 the mass of the sun would live for 10 trillion years. And so it's a little bit counterintuitive if you're only thinking about the numerator. But once you remember the denominator, it makes a difference. An analogy people often make is imagine that you go to a casino and the red dwarf is like the cheapskate that doesn't have a big bankroll, but they spend their money very, very slowly, playing nickel slots, penny slots, not really gambling very quickly, and they're there for a long amount of time in the casino before they go bankrupt. Whereas the multimillionaire comes in, and they've got a big bankroll, but they burn through it so quickly, making $1 million bets every few minutes, that they're out of there half hour later. So think about the red dwarfs as being very frugal with the energy that they have available to them. Any follow-up question on that or comments? Okay, in the final few minutes here, I wanted to share with you some of the images from your book. In fusion, what do you have to have happen? We're going to talk about the proton-proton chain more next time. But the idea is that you've got to get protons close enough together to one another that they can overcome their repulsion. And at first glance, that is rather surprising that it happens at all. Because you imagine that as two protons get closer and closer together, they're both positively charged, so there's this gigantic potential energy barrier that they are facing. And unless they're moving fast enough, then they never get close enough for the strong force to bind them together. But if you look at this graph here, it has a peak at roughly around 1 Fermi, 1 femtometer. A femtometer is 10 to the minus 15 meters. And then it plummets downward. If you can get the two particles to be within 10 to the minus 15 meters of one another, then the strong force can bind them together. And this is how deuterium gets made, which is heavy hydrogen. Deuterium has 1 proton and 1 neutron in it. The two protons come together, and if you calculate the energy that's necessary to overcome this repulsion, what you find if you do it naively without quantum mechanics is that the temperatures you need are on the order of 10 to the 10 Kelvin. That's what's done in your book here in chapter 10. You figure out what the kinetic energy is to overcome the barrier of repulsion. You figure out the temperature associated with that average kinetic energy, and you find it's 10 to the 10 Kelvin. The central temperature of the sun is only 15 to 16 million Kelvin, much less than this 10 billion Kelvin. And so what the answer here is that quantum mechanics allows you to, if you get the particles within a de Broglie wavelength of one another, that's good enough, right? It allows you to do what's called quantum tunneling. And even though classically these two protons coming toward one another wouldn't have enough energy to make it over this barrier, quantum mechanics gives you a non-zero chance that they can penetrate that barrier and be merged together as one. The final thing I'll show you here is this is the proton-proton chain. That's the overall reaction there at the top where 4 protons make helium and other things. And next time we'll talk a little bit about the individual steps that go into that proton-proton chain. That's how hydrogen is being converted into helium in the cores of stars like our sun. Any final questions or comments for today?
I have a quick question. What's the reading quiz?
How about if you take away the SIO, fusion is fun. So the answer to today's reading quiz is if you take away the SIO, fusion is fun. Other comments and questions?
I have one quick question. It has to do with brown dwarfs which don't get to be stars. What's the critical point for tunneling to occur? I'm just wondering what the barrier is there.
What's related to, and it's on pages that I had you skip from the reading. So if you want to go back and answer this more carefully, you can read about the Gamow peak, which is roughly page 300 and something right in there. But there's a figure somewhere around figure 10.5, 10.6, which is the Gamow peak. And what's going on is you've got to have particles that are on the tail end of the Maxwell-Boltzmann distribution for speed. So of all the particles that are moving, you get the ones that are just moving fastest, right? But remember that you have fewer and fewer of those particles that are moving faster. So there's two competing effects, right? There's more particles that are moving slower, so you got to take into account that you're more likely to have them. But those ones that are moving slower are less likely to react. The ones that are moving faster are more likely to react. So you have to find the sweet spot in the middle there, and that's what the Gamow peak represents. And what you find is that Gamow peak, in order to have significant amounts of fusion, you need to have temperatures of about 10 million Kelvin. There's an approximate or rough or slight dependence on density, but it's not too sensitive on density. It's about 10 million Kelvin. And if your brown dwarf cannot achieve that 10 million Kelvin threshold in its center, then it is a brown dwarf and it can't become a star. If the object that's collapsing is able to achieve that 10 million Kelvin threshold, then it can become a star.
Okay, thank you.
All right, so we are out of time. Thanks for sticking around a few extra minutes. I'm going to stick around a longer too in case any of you have questions, but have a good day.